Welcome back to the deep dive. Today we are swapping the usual maps and charts for something, well, a bit more dazzling.
Planetary treasures, you could say.
Exactly. We're going deep into gemology, using what's really the foundational source, the GIA Gem Encyclopedia.
That's right. And for anyone curious about, how the Earth cooks up these tiny, incredibly valuable things, the GIA's framework is, well, it's the gold standard.
It gives us the science, the language for it all.
Yeah, composition, rarity, grading, all that. So our goal today really is to give you a shortcut, a good synthesis of the science and the stories behind, over 24 gems?
Yeah, focusing on the surprising facts, the history, it's all in there.
And we should probably stress this source, the Gemological Institute of America, GIA. It's not just some book.
No, it's the global authority. They set the technical standards. The whole industry kind of relies on them.
They do the serious science, analysis, and grading. They provide the high-tech instruments.
Like that GIA face-to-wear for analyzing cut.
Right. And they manage the whole process, like report check and submit a gem to their labs worldwide. It's serious business.
So the encyclopedia we're using, it's built on all that authority. We're basically using their master catalog of Earth's treasures as our map today.
Exactly. And that map, right away, it lays out the big categories. They divide the gem world into 5 main areas.
Okay, what are they?
You've got natural diamonds, then natural fancy color diamonds, different laboratory grown diamonds, which is a really key distinction these days. Then basically all other colored stones lumped together, and finally pearls, organic gems.
And what's really useful for you listening is that this isn't just for scientists in labs. This framework is what they teach globally.
Absolutely. If you want to be a pro, you get GIA certified, like the graduate gemologist diploma.
Or the more specialized ones, graduate diamonds, graduate colored stones.
Yep, even their business credential, the applied jewelry professional, it's all built on the same core knowledge base.
Yeah.
Connects the lab, the classroom, the shop floor.
Right, so everyone's speaking the same language, whether you're in London or, Bangkok.
Precisely. Consistency.
Yeah.
Okay, so where do we start this deep dive? Has to be diamond, right? The element of purity.
Let's do it. We hear diamond, we think sparkle, maybe cost. But the core fact is pretty amazing, isn't it?
It really is. Just one element, carbon. That's it. Pure carbon.
The purest gem.
And that purity leads directly to its famous properties.
Yeah.
The structure is everything. It's this giant network where carbon atoms are locked perfectly together.
A tetrahedral lattice, I think they call it.
That's the one. Super rigid, super strong, and that's why it's the hardest natural thing we know. Unbeatable durability.
We sort of take the colorless aspect for granted, too. But the source flags the age. These things are ancient.
Oh, absolutely primeval.
Yeah.
Most diamonds are over 1 billion years old. Some much older.
1 billion years. How does that connect to how they actually form?
It's all about geology, deep Earth geology. They form way down, maybe 100 miles deep in the Earth's mantle, under unbelievable pressure and heat.
So they cook down there for ages.
For geologic time, yeah. Billions of years, sometimes, just sitting there. Until, bang, a specific kind of deep volcanic eruption happens.
Kimberlite pipes. Lamprite pipes.
Those are the ones. They basically act like express elevators rocketing the diamonds up to the surface in just, hours. It's pretty violent.
Wow. So billions of years forming, then a super fast ride to the surface. That timescale difference is kind of mind-blowing when you think about human history.
Totally. Puts the value in perspective, doesn't it?
Right.
A billion-year-old chunk of pure carbon crystal.
It does. But okay, colorless diamonds are the standard. But the really rare ones, the super expensive ones, they're the opposite, right? They have color, fancy color diamonds.
Exactly. It's a total flip. Colorless diamonds are graded on lack of color, fancy colors. It's all about the intensity of the color, the saturation.
And statistically, these are the rarest and priciest.
By far.
Yeah.
Of all gemstones, rarest and most costly.
And the color comes from tiny flaws, other elements sneaking in.
Pretty much.
Yeah.
Tiny structural defects or trace elements getting into that carbon lattice. Like a bit of nitrogen causes yellow. Boron gives you that famous blue.
Right. And the famous ones are legendary. The source mentions the Hope diamond.
Ah, the Hope. That huge, deep blue stone.
Yeah.
Probably the world's most famous single jewel. Amazing color, crazy history.
And the graph pink.
Yeah, an incredibly vivid pink diamond. When the GIA info was compiled, it held the record. Most expensive gem ever sold at auction.
So you go from valuing purity in colorless diamonds to valuing intense color caused by impurities in the fancies? Quite a switch.
It's a fascinating market dynamic driven by rarity and aesthetics.
Okay, so we've done carbon. Now let's shift gears. Away from pure chemistry into how gems play with light. This is where it gets really interesting, I think.
Oh yeah, phenomenal gems. Their value comes from optical effects, stuff happening inside the stone because of its structure.
Right, like opal,
Yeah.
famous for that shifting kaleidoscope of colors.
Yeah.
The source uses amazing words for it. Fireworks, jellyfish, galaxies, lightning.
And those aren't just fancy marketing terms. They actually describe different patterns of how the color moves and flashes across the stone's surface.
So what's the physics behind that? It's not trace elements this time.
Nope. Opal is technically hydrated amorphous silica, so silica and water. But the magic is its internal structure. It's made of these microscopic silica spheres, all packed together in layers.
Tiny balls of silica.
Exactly. And when they're stacked up really neatly in an orderly grid, the whole structure acts like a diffraction grating. It splits white light into spectral colors.
Like a prism does.
Sort of, yeah, but through diffraction. And the size of the spheres and how regular the stacking is determines which colors you see and how they play. That's the play of color.
So the patterns, jellyfish or lightning, depend on how perfect that stacking is.
Pretty much. How uniform the spheres are, their size. It's all about the microscopic architecture. Structural color, not pigment.
That's cool. Architectural color. Okay, contrast that with moonstone.
Yeah.
Much softer effect, right? That sort of ghostly glow.
Yeah, that's called agilurescence. It's like a billowy blue-white sheen that seems to float just under the surface. It moves as you turn the stone.
Almost like captured moonlight. I can see why the Art Nouveau designers loved it, that flowing, ethereal look.
It was absolutely a favorite for them, that softness, that subtle glow. And the cause is different from opal. Moonstone is a type of feldspar.
Right.
And inside, it has these incredibly thin, alternating layers of two different types of feldspar. Microscopic layers. Light hits these layers and scatters.
And that scattering creates the sheen.
Specifically, the layers scatter the short wavelength blue light most effectively,
Yeah.
creating that signature blue shimmer or
Okay,
schiller.
subtle scattering, then there's sunstone. Same feldspar group, but way more energetic looking, right? That glittery effect.
Definitely. Sunstone shows eventurescence. It's a distinct, lively sparkle coming from within the stone.
So what's causing the sparkle there? Not layers, presumably.
No, this time it's tiny, flat mineral inclusions suspended inside the feldspar, usually little platelets of hematite or maybe goethite.
Like microscopic mirrors?
Kind of, yeah. When light hits these tiny reflective plates, they flash and glitter, gives it that sunny sparkle.
And sunstone can be different types of feldspar, orthoclase or plagioclase.
That's right. Both are feldspars, part of that big mineral group.
Does that difference, orthoclase versus plagioclase, matter much to someone who isn't a geologist?
Well, chemically, they're slightly different. Orthoclase is a potassium feldspar. Plagioclase is more sodium and calcium based. It affects, where and how they form geologically. But for the gem itself, the key thing is the eventurescence. That's what makes it sunstone, regardless of the exact feldspar type. It highlights the complexity, though.
It does. Okay, that structural complexity is a nice lead into talking about a really famous mineral species, beryl.
Ah, yes, the beryl family. If you're learning gemology, you have to know beryl. It gives us some truly iconic gems.
Chemically, they're all the same base mineral.
Pretty much. Beryl is beryllium aluminum cyclosilicate. Kind of a mouthful. But the magic happens when tiny amounts of other elements sneak into that crystal structure during growth.
And depending on the element, you get different colors, different gems.
Exactly. The big three cousins are emerald, aquamarine, and morganite. All beryl, just with different trace elements giving them color.
Let's start with the star emerald. That deep, rich green, synonymous with like ancient treasure.
Totally. It's the most valued beryl variety. That intense blue-green to pure green color is its defining feature.
And what gives it that specific color?
Trace amounts of chromium, mostly. Sometimes vanadium, too. Get the concentration just right, and you get that vivid emerald green. If it's too pale or the wrong hue, it's just called green beryl, not emerald. The name carries weight.
And the history is just immense. Cleopatra, the Incas, the Moguls.
Oh, yeah. Cleopatra supposedly loved emeralds, had her own mines. The Spanish conquistadors found huge quantities in South America, where the Inca rulers already treasured them. Mughal emperors in India carved them, pharaohs in Egypt. It was prized everywhere.
Where do the best ones come from today?
Historically, Colombia's been famous, but good sources are also found across Africa, like Zambia, and parts of Central Asia, Brazil too. That emerald green really is the color of old money and power.
Okay, then the next beryl cousin, aquamarine. The name says it all right. Water of the sea.
Perfect name. It captures that clear blue to slightly greenish blue hue, beautifully.
Different trace element this time.
Yep. Aquamarine gets its color from trace amounts of iron within the beryl structure.
And aquamarine is known for forming huge crystals sometimes.
It really is. Beryl crystals can grow into these massive clear columns. The source notes that sometimes they're big enough to cut gems over 100 carats. Clean, faceted gems.
Imagine the size of the original rough crystal for that. Must be enormous.
Truly impressive. A very different vibe from emerald. More serene, maybe.
And the third main beryl, morganite, the pink one.
That's it. Morganite is the pink to sort of orange-pink variety. It's sometimes just called pink beryl.
And the color comes from, let me guess, another trace element.
You got it. This time it's manganese. Just a tiny trace sneaks into the crystal lattice and causes that delicate, subtle blush.
It's a softer color than emerald or even aquamarine sometimes. More subtle.
It is. Often described as having a warm tone. It's a great example, though. Intense green, clear blue, soft pink. All fundamentally the same mineral structure, just tweaked by chemistry.
Amazing. Okay, that covers the beryl family. Let's move into section 3. We're talking more wild chemistry, color change phenomena. This is cool stuff.
Right, starting with maybe the most dramatic trick in the gem world, alexandrite.
The color change gem.
Exactly. It's a variety of a different mineral species called chrysoberyl. And its color change isn't subtle. It's like, whoa.
How does it work? What colors are we talking about?
In daylight or fluorescent light, it looks bluish green. But take it under incandescent light, like an old light bulb or candlelight.
Yeah.
And it shifts dramatically to a purplish red. It's a complete transformation.
Like having two different gems in one ring. That's incredible. What's the science there? How does it do that?
It's fascinating.
Huh?
It also involves chromium, just like emerald. But in alexandrite's specific crystal structure, the way chromium absorbs light is really unusual. It strongly absorbs yellow and some green light.
Okay.
So in daylight, which has a balanced spectrum with plenty of blue and green, the gem lets those wavelengths pass through, so we see green or blue-green.
Makes sense.
But incandescent light is poor in blue-green and rich in red light. So when you put alexandrite under that light, there's not much blue-green for it to transmit. Instead, it transmits the red wavelengths. It doesn't absorb as strongly. Result, it looks red.
So the gem itself doesn't change, just how it interacts with the type of light hitting it.
Precisely. It's a slave to the light source. And because that effect is so dramatic and rare, combined with chrysoberyl being pretty durable, top-quality alexandrites are incredibly rare and valuable.
Wow. Okay. From color change magic to a gem known for, well, for pretending to be something else for centuries. Spinel, the great imposter.
A great nickname and well-earned. For a very long time, especially large red spinels were mistaken for rubies.
And not just any rubies, right? Some ended up in crown jewels.
Absolutely. The source highlights two mega-famous examples, the Black Princess ruby and the British crown jewels.
That huge red stone at the front of the imperial state crown.
That's the one, not a ruby. It's a massive, historic spinel. And the Timur ruby, another legendary stone in the British collection, also inscribed with the names of Mughal emperors, also a spinel.
Why the confusion? Do they look that similar?
They can, especially the red ones. They often form in the same geological deposits. They're both very hard, brilliant stones. It took advances in gemological science to reliably tell them apart.
But spinel isn't just an imposter anymore, is it? It's valued in its own right now.
Oh, absolutely. Gem collectors love spinel. It has fantastic clarity, brilliance, and it comes in a whole rainbow of colors, beyond red, vibrant pinks, purples, oranges, and especially stunning blues, like cobalt blue spinel. It definitely stands on its own merits today.
Okay, that history of confusion leads us perfectly to the mineral spinel was mistaken for corundum. This is the real powerhouse species, right? Giving us ruby and sapphire.
Exactly. Corundum is aluminum oxide. In its pure form, it's colorless. But add trace elements, you get treasure.
And ruby is the red version, the most valuable corundum.
Traditionally, yes. That rich, saturated red color comes from, guess what? Trace amounts of chromium replacing some aluminum in the crystal structure.
Chromium again. It seems to be the magic ingredient for red and green gems.
It's a key chromophore,
Yeah.
in the history of ruby. Wow. This source mentions its ancient Sanskrit name, Naraj.
Meaning?
King of precious stones. Tells you everything, doesn't it? Millennia ago, they knew this stone was special. Supreme value.
And that reputation comes from its color, but also its hardness.
Definitely. Corundum is a 9 on the Mohs hardness scale. Only diamond is harder at 10. So ruby is incredibly durable, suitable for any kind of jewelry. Plus, it has that exceptional color. It's the king for a reason.
Okay, so if corundum is red, it's ruby. What if it's any other color?
Then it's sapphire. Simple as that. The term sapphire technically applies to any corundum that isn't red.
Oh, well, we usually think of sapphire as blue.
That's the classic, yeah. And that iconic blue color comes from trace amounts of iron and titanium working together in the crystal lattice.
But sapphires can be other colors, too.
Oh, yes. A huge range. Add different trace elements or combinations, and you get yellow, pink, orange, like the rare pepperacha sapphire, green, purple, even colorless sapphire. These are often called fancy sapphires.
So corundum is like a chemical chameleon.
Pretty much. It's amazing how just a few atoms per million of a different element could totally change the color and value.
And sometimes sapphires show that star effect, asterism.
Right. If the corundum crystal grew with lots of tiny needle-like inclusions of another mineral, usually rutile.
Rutile, titanium dioxide.
Yep. And if those needles are oriented perfectly along the crystal's axis, and then you cut the stone, as the cabochon, that smooth, domed shape.
No facets.
Right. Then light reflecting off those oriented needles creates a six-rayed star that seems to glide across the surface as you move the stone. Star sapphire.
Yeah.
Or star ruby, if it's red corundum.
That's a combination of chemistry, crystal growth, and the cutter's skill.
Absolutely. A phenomenal effect.
Okay, so corundum represents the peak of rarity and value in many ways. Let's shift now to a mineral that's almost the opposite in terms of abundance. Quartz.
Ah, good old quartz. Silicon dioxide, one of the most common minerals on Earth's crust.
But common doesn't mean boring, right? Quartz gives us some really popular and beautiful gems. It shows rarity isn't the only thing that matters.
Not at all. Quartz varieties are hugely important commercially and historically, all thanks to impurities giving them color.
And the most famous quartz, probably amethyst, the purple one.
Definitely the most recognized. That beautiful purple to violet color. The source has a great line about it. Beautiful enough for crown jewels, yet affordable enough for class rings.
That sums it up perfectly. High-end appeal, but accessible. What causes the purple?
It's mainly trace amounts of iron impurities within the quartz crystal, combined with natural radiation exposure over geologic time during its formation.
And amethyst often forms those big, six-sided crystals you see in geodes.
Yes, very commonly. Found in volcanic rocks, geodes. Major sources are in South America, like Brazil and Uruguay and parts of Africa. Its abundance keeps it affordable.
Okay, closely related. Citrine, the yellow to orange quartz.
Right. Also gets its color from iron impurities, similar to amethyst, but may be formed under different temperature conditions or treated later. Sometimes amethyst is actually heat-treated to turn it into citrine.
Really? They heat the purple stuff and it turns yellow.
Often, yeah. Natural citrine is actually quite rare compared to amethyst. Most commercial citrine started as amethyst, but it's a very popular sunny, warm-colored gem. A great alternative if you want yellow but can't spring for, say, a yellow sapphire.
Makes sense. Okay, this is wild. What about ametrine? Is that amethyst and citrine?
In the same stone, yes. Ametrine is one of the rarest types of gem quartz because it naturally shows both the purple of amethyst and the yellow to orange of citrine within a single crystal, zones of color.
How does that happen naturally?
It's thought to be caused by different temperature zones across the crystal as it was growing, or maybe variations in the oxidation state of the iron impurities. One part forms under conditions for purple, another part under conditions for yellow-orange.
So you get this amazing bicolor effect, nature's own half and half.
Exactly. Very cool stuff. Bolivia is the main source for that.
And the last main quartz we should mention is rose quartz.
The delicate pink variety. Unlike amethyst and citrine, which are usually transparent, rose quartz is typically translucent, kind of milky.
And the color isn't from trace elements this time.
Generally not. The pink color and the cloudiness usually come from microscopic fibrous mineral inclusions scattered throughout the quartz. Maybe minerals like dumortierite or even rutile.
So it's more about tiny included fibers scattering light and giving it that soft pink look.
That's the common understanding for the translucent stuff used in beads and carvings. But the source does mention that actual transparent, well-formed pink quartz crystals do exist. They are much rarer and more valuable, colored perhaps by different mechanisms involving aluminum or phosphorus.
Interesting distinction. Okay, we've covered gems defined by purity like diamond, by structure like opal, by big families like beryl and quartz. Now let's head into section 4. This focuses on gems tied to really extreme geology, unique places, or deep time.
Right. Some gems are special because of where or how they form. Let's start with peridot. The GIA calls it the extreme gem.
And for good reason. Where do we find this stuff? It's pretty wild.
It really is. Peridot is the gem variety of the mineral olivine, is that lovely yellow-green to olive-green color.
Yeah.
And you find it, yes, in volcanic lava flows, sometimes as nodules brought up from the Earth's mantle,
Deep earth stuff.
but also incredibly inside certain types of meteorites.
Meteorites, like from outer space.
From outer space, specifically palisite meteorites, which are these stony iron mixtures. They often contain crystals of olivine, gem-quality peridot embedded in the metal matrix.
So peridot is one of the few gems we know for sure has extraterrestrial origins, too.
Confirmed. It forms under high temperatures, deep in the mantle, yes, but also during the formation of asteroids or other planetary bodies early in the solar system's history. Pretty extreme.
Wow. Okay, from cosmic origins to a gem defined by being found in only one place on Earth, tanzanite.
Yeah, talk about unique locales. Tanzanite is only found in a very small mining area in northern Tanzania near the foothills of Mount Kilimanjaro. That's it. Nowhere else.
That geological restriction must make it inherently rare?
Absolutely. It's a finite resource. It was only discovered relatively recently in 1967 and named after its home country. It shot to popularity very quickly.
And it's that blue-violet color.
It's the blue to violet or purple variety of a mineral called zoisite. Most tanzanite is actually heat-treated to enhance that desirable blue-violet color.
Yeah.
The natural stone often has brownish or yellowish tones that heating removes or modifies. But the result is that stunning, unique hue.
Okay, another one tied to specific harsh conditions. Turquoise.
Right. Prized for centuries for that intense sky blue or robin's egg blue color, sometimes greenish blue.
What kind of environment does turquoise need to form? It's not volcanic, right?
No, it's a secondary mineral. It's a phosphate of copper and aluminum. It forms when water, usually acidic groundwater, percolates down through copper-rich rocks in, crucially, very dry, arid environments.
So you need copper, you need water to move things around, but you need it to be generally barren and dry overall.
Exactly. It only forms in the Earth's most arid regions. That scarcity of water is key. Think deserts, basically.
And the history reflects that. Ancient Egyptians used it. King Tut's mast has turquoise inlay.
And Mesoamerican cultures like the Aztecs prized it highly, as did early Chinese dynasties. It pops up in jewelry and artifacts from dry regions across the globe, often associated with protection or status.
Fascinating. Okay, shifting from extreme geology to, like, deep time capsules. Amber.
Nature's time capsule is the perfect description. Amber isn't a mineral at all. It's fossilized tree resin.
Just ancient, sticky stuff from trees.
Pretty much. Resin oozed out of trees millions of years ago, often 20 to 50 million years old, sometimes much older, and as it flowed, it trapped things.
Like insects. That's the classic image.
Insects, spiders, pollen, bits of leaves, air bubbles, sometimes even tiny lizards or frogs, and the resin hardened over millions of years, perfectly preserving whatever got stuck inside.
So it's literally a window into ancient ecosystems. Amazing.
It really is. Paleontologists love it.
Okay, now let's talk about rocks that are gems, not just single minerals, aggregates, like lapis lazuli.
Right. Lapis isn't a single mineral. It's a metamorphic rock. A beautiful, deep blue rock.
What's it made of, then?
It's primarily composed of the mineral lazurite. That's what gives it the intense blue. But it usually also contains streaks or patches of white calcite, and often these glittering golden flecks of pyrite iron sulfide.
Fool's gold.
Yep. But in lapis, those golden specks are actually considered desirable. Part of its characteristic look. Adds a bit of sparkle to the deep blue.
And the best lapis comes from?
Afghanistan. For thousands of years, the source says over 6,000 years, the mines in the Badakhshan province of Afghanistan have produced the world's finest, most intensely colored lapis lazuli. It's legendary.
Wow. Okay, another important aggregate or maybe group term is jade.
Yeah, jade is tricky because the name actually covers two different silicate minerals, nephrite and jadeite. And sometimes a third green omphacite gets included too.
But culturally, jade is huge, right? Especially in Asia.
Immense. Perhaps more culturally significant than any other stone in certain parts of the world. In China, jade, especially nephrite historically, was revered, carved into ritual objects, like the Bai disc, a pierced disc symbolizing heaven. It represented purity, wisdom, justice.
And in the Americas, too.
Yes, the Aztecs and Mayans highly valued jadeite, the other main type of jade. They considered it more precious than gold, using it for masks, tools, and ornamentation.
What's the main difference between nephrite and jadeite? They look similar sometimes.
Chemically and structurally, they're different families. Nephrite is an amphibole, generally found in more opaque, darker greens or creamy whites. It's incredibly tough because its structure is like tightly interwoven fibers. Jadeite is a pyroxene. It can be harder and sometimes occurs in much more vibrant greens, lavenders, even reds, and can be more translucent. The highly prized imperial jade is jadeite.
So two different minerals sharing one famous name and a lot of cultural weight.
Pretty much. Both require specific metamorphic conditions to form.
Okay, we're nearing the end, but there's still several important gems to touch on. Let's group some of the remaining ones. How about iolite?
Iolite. Geologists call it cordierite. It's known for its lovely violet blue color, but its really cool feature is strong pleochroism.
Meaning it looks different colors from different angles.
Exactly. Look through one direction of the crystal, it might be intense blue-violet. Turn it 90 degrees, it might look almost colorless or yellowish gray. Turn it again, maybe a different shade of blue. Very distinct shifts.
And the legend connects to that, right? The Vikings.
Yeah, the story goes the Viking navigators used thin slices of iolite as polarizing filters. By looking through it at the sky, they could supposedly pinpoint the sun's exact position even on overcast or foggy days because of how it interacted with polarized light.
A natural compass filter. Cool. Okay, next. Tourmaline. The source says it has one of the widest color ranges of any gem.
It really does. Tourmaline isn't a single mineral, but a complex group of boron-silicate minerals. Its chemistry is incredibly variable. It can grab onto iron, magnesium, sodium, lithium, aluminum, all sorts of things.
And that leads to lots of colors.
Pretty much every color imaginable. Pinks, reds, rubellite, greens, blues, indicolite, yellows, browns, black, schorl, and often multiple colors in the same crystal.
The watermelon tourmaline. Pink inside, green outside.
That's a classic bicolor example. You can get tricolor too. But the really exciting recent discovery, relatively speaking, was in Paraíba, Brazil.
Ah, the Paraíba tourmaline. Neon blue-green.
Exactly. An absolutely electric, vibrant blue or green color, unlike any other tourmaline. It's caused by trace amounts of copper, which is very unusual for tourmaline.
And that makes it super rare and valuable.
Extremely. Similar copper-bearing tourmalines have since been found in Africa, but that Paraíba material set a new standard for intensity and price.
Got it. Okay, how about zircon? Sounds like cubic zirconia, but it's not, right?
Definitely not. That's a common, unfortunate confusion. Cubic zirconia, or CZ, is a man-made diamond simulant. Zircon is a natural gemstone, zirconium silicate, and it's beautiful.
What's its main feature?
High refractive index and strong dispersion. Dispersion is the gemological term for fire, the ability to split white light into flashes of spectral color, like a diamond does. Zircon has very strong fire.
What colors does it come in? I think of blue zircon.
Blue is probably the most popular, and that's often created by heat-treating brown zircon. But natural zircon also comes in beautiful yellows, oranges, reds, reddish browns, and greens. It's a very brilliant gem.
Good to clear up the CZ confusion. Next, topaz. Another one with lots of colors.
Yep. Topaz is an aluminum silicate, but with fluorine and hydroxyl in its structure. Color-wise, it spans honey yellows, fiery oranges, pinks, reds, and famously blues.
But the blue is often treated.
Very often. Most of the affordable bright blue topaz on the market is actually colorless topaz that's been radiated and then heated to produce the blue color. It's stable and popular.
But natural colors exist too and are more valuable.
Well, yes. The naturally occurring imperial topaz, those rich golden orange, peach, pink, or cherry red colors, are much rarer and highly prized, especially the pink to red hues.
Where do those rare ones come from?
Historically, the Ural Mountains in Russia were famous. Today, Ouro Preto in Brazil is the main source for imperial topaz.
Okay, nearly there. Garnet. Another group name, not a single stone.
Exactly. Garnet refers to a whole group of closely related silicate minerals. They share a similar crystal structure, but vary quite a bit in chemical composition.
And that means lots of colors again.
Almost every color except pure blue. You've got the classic deep red garnets like pyrope and almandine. You have vibrant orange spessartine. You get greens like savorit, a type of grossular garnet, and demantoid and androdite garnet. Yellows, purples, pinks, even color change garnets exist.
Wow, so garnet is super versatile. Are any particularly rare?
The bright green ones, savorit and demantoid, are quite rare and valuable. Demantoid is especially prized because it has fire, dispersion, even higher than diamond sometimes. Savorit is a beautiful, vivid green alternative to emerald.
Lots of options in the garnet family. Okay, one more mineral. Kunzite. A newer one.
Relatively speaking, yes. It was identified as a distinct gem variety of the mineral spodumene in the early 1900s and named after the famous gemologist George Kunz.
It's the pink one.
Pink, to lilac or violet. It's a lithium aluminum silicate, and like morganite, it gets its delicate color from trace amounts of manganese.
What's it known for?
Often found in quite large transparent crystals. It can show strong pleochroism, different shades pink-violet from different directions, but it can also fade in prolonged sunlight, so needs a bit of care.
Good to know. Okay, we've covered a huge range of minerals, but we need to close the loop with the major exception, the organic gem, pearl.
Right. Everything else we discussed was crystalline, formed by geology. Pearls are fundamentally different. They're created by life.
By oysters and mussels.
Exactly. Marine oysters and freshwater mussels. They form inside the body of these mollusks, either naturally as a reaction to some irritant that gets inside the shell.
Like the proverbial grain of sand.
Could be. Or a parasite or something else. The mollusk coats the irritant with layers and layers of nacre, the same stuff that lines the inside of its shell. Or they can be cultured.
Where humans intentionally introduce an irritant to stimulate pearl growth.
Precisely. Most pearls on the market today are cultured pearls. Natural pearls, formed completely without human help, are incredibly rare and often very expensive.
But chemically, they're the same stuff, nacre.
Yes, nacre is composed mainly of calcium carbonate in the form of microscopic aragonite crystals held together by an organic glue called conchiolin. It's the layering of these tiny crystals that gives pearls their characteristic luster and orient, that subtle iridescence.
So no digging, no heat and pressure, just biology. They really are unique.
Totally unique. Smooth, lustrous, classic symbols of elegance. A whole different category.
Okay, wow. We've covered a lot. From pure carbon formed billions of years ago to light-bending silica spheres, trace elements creating rainbows in beryl and corundum, fossilized resin, and now biological gems. What's the big takeaway from this journey through the GIA Encyclopedia?
I think it really hammers home the diversity. How tiny changes in chemistry, like a little bit of chromium turning aluminum oxide into ruby, or changes in microscopic structure, like those spheres in opal, create this huge spectrum of beauty, rarity, and value.
It's all about the details.
Exactly.
Yeah.
And understanding those details, having that foundational knowledge that GIA provides, is what lets us differentiate these materials, appreciate them, and ultimately value them. Knowledge is absolutely key in the world of gems.
And for you listening, remember, this knowledge base isn't static. GIA is constantly doing research, publishing its Gems and Gemology journal, maintaining a huge library. The discovery is ongoing.
It really is. New finds happen, treatments evolve, scientific understanding deepens. It's a dynamic field, like when those perihebat tourmalines hit the market to change things.
It certainly did. So as we wrap up this deep dive, here's a final thought to maybe leave you with. We talked about peridot being found in meteorites.
Yeah, the extreme gem.
Right. So some of the beautiful, valuable materials we cherish that end up in jewelry weren't just formed deep inside our planet. Some literally fell from the sky, remnants from the birth of the solar system itself.
Cosmic contributions to our jewelry boxes.
Exactly. So maybe next time you look at a gemstone, think about the incredible journey it took. Whether it was billions of years in the mantle, a million years as tree sap, or maybe even a trip across interstellar space, it connects us to something truly vast and ancient.